Uh, hi, good morning and good afternoon, everybody. Request everybody to be on mute, please. Yeah, again, thank you everybody for joining us today and welcome to the webinar on the use of raw materials for hydrogen production. We are hosting this in collaboration with Brussels and the Consulate General of Belgium in Mumbai, and of course, Global Business Inroads. We'd like to welcome Mr. Pierre-Emmanuel Brussels, the Consul General of the Kingdom of Belgium in Mumbai, and Dr. Amit Varma, the Director of Energy at EPIO. Welcome to both of you. Just a quick, introduction about GBI. So we are a technology and innovation management consultancy.
Yes, sir. Actually, I'm in a meeting. Maybe after 1 hour.
Yeah, just going back. So we are primarily focused on sectors related in terms of technology and knowledge and innovation transfer. We work with sectors related to the UN SDGs. And over the last 12 years, we have supported about 200 plus organizations in various capacities, focused on looking at accessing the Indian market as well as helping a lot of Indian companies access international markets as well. Today, we're happy to be collaborating with Brussels to promote Umicore and Solvay from Belgium. They have very specific solutions that are supporting the government of India's national hydrogen energy mission that was launched in 2021. And we will be looking forward to hearing from them as well and what kind of work that they're doing in India. And if anybody would like to reach out to the two companies, Mr. Fitries and Vincent, please feel free to contact us at Global Business Inroads. Next slide, Atina. So we have a very interesting agenda for you today, and we have very distinguished speakers from Belgium as well as India. And with that, I would like to invite Ms. Christine Monia, the area manager for Asia at Brussels, at Hub Brussels. Christine, over to you.
Thank you, Arsha, for the kind introduction, and good morning, everyone. Welcome to the webinar that we co-organize with GBI on hydrogen. I am, as Arsha mentioned, working as area manager for Asia at Hub Brussels. This means that I help out Brussels-based companies to export to the Asian continent, including India. I will tell you a little bit more about the Brussels capital region, and it's linked to renewable energy and hydrogen. So the Brussels capital region has a target to reduce greenhouse gas emissions by 40% by 2030. So it's pretty close. And to get close to the European carbon neutrality target by 2050. And
response नहीं आया मैं बात करता हूँ ठीक है
Would you please mute yourself? Thank you. So how does our capital plan to reach those targets is by diminishing non-renewable energy sources and promoting the use of renewable energy, to develop also a passive housing to reduce energy consumption in general, to diminish the impacts, the environmental impact of transportation, and also to be a good example in the country. So I mentioned renewable energy in general. Brussels is a small region, so we have some weakness when it comes to renewable energy. We have no potential for wind energy because the airport is really nearby. We have no potential for hydroelectrical power, no biofuel production as we are a big city, and strict rule for biomass. But we have potential for renewable energy development. We have a well-developed grid that allows a lot of production and development. There is a good potential for rooftop solar and biomethanization. Now, how about hydrogen? There is currently a project going on from the Public Transports Administration. There is a bus. I've been muted. So bus running on hydrogen in the city is being tested since last year. And if the conclusion of the test is positive, there will be a switch from fuel running buses to hydrogen buses. So the future in hydrogen in Brussels will be, the future of transportation, in Brussels will be hydrogen. And you will also discover the potential of our companies in a few minutes. Thank you for your attention, and back to you, Arsha.
Great. With that, I think I would like to invite Mr. Pierre-Emmanuel, the Consul General for Belgium in India. Mr. Pierre, over to you. You're muted.
Thank you, Harsha. Do you hear me now?
Yes.
Thank you, Knizelin. Distinguished ladies and gentlemen, I'm very happy and it's a great honor for me to welcome you all to this webinar, of course, on the topic of green hydrogen, but more specifically focused on the use of raw materials for hydrogen production. Now, we all know renewables, green energy, clean technology have all become common language, as we are all aware that we have to work together to fight and to act against climate change, to reduce carbon emissions, and of course, to save our planet and humanity from disaster. Now, green hydrogen is clearly a part of the solution, and all around the world, countries as well as companies have started to act, of course, at various speeds, but they have started to act to develop the technology, but also to create the conducive business environment to set up production facilities. Now, at the Consulate, our journey with green hydrogen started in October 2021, when we organized the first Belgo-Indian conclave on green hydrogen economies. It was a successful initiative, and it was showcasing the Belgian expertise in this new and growing sector by bringing together policymakers from Belgium and India to discuss our respective governments' initiatives to support, promote, and develop those technologies. But we also were happy to, and we were first, of course, honored to host the Belgian Minister of Energy, Her Excellency Mrs. Tine van der Straten, and we had the pleasure to also host, of course, the CEO of NHEM, Shri Amitabh Kantji. While at the same time, it was important for us to bring together major players, industrial players of Belgium and India, and I would like to mention John Cockerill, DEME, Tractable, Reliance, ONGC, Renew Powers, and they were able to showcase their projects, their realizations, and their plans for the future. Now, today, we will go a little bit deeper into understanding how two Belgian companies, Umicore and Solvay, as you have already mentioned, can provide solutions to support the targets of the India National Hydrogen Energy Mission. Now, for those which are not yet familiar with those two global players, Umicore is a global materials technology and recycling group. It holds a unique position in clean mobility solutions and in the recycling of precious metals. Solvay, on the other hand, is a 159-year-old chemical company with a focus on materials and solutions used in sectors such as automotive, aerospace, agriculture, consumer goods, healthcare, and electronics. Both companies have been very active in India for many years and have plants near Vadodara and Pune. And they are now looking to become part of India's clean mobility / clean energy story with battery and fuel cell materials. Likewise, I look forward to hearing the views of Mr. Amit Verma as he takes us through NHEM's role in helping India navigate its renewable energy landscape. Ladies and gentlemen, as we've seen, there is a trend away from fossil fuels and towards renewable forms of energy production and storage. The world population is growing steadily and requires more and more energy, especially in the course of the ongoing urbanization and digitalization of our lives. The environmental awareness of consumers and companies has also changed. Today, more people are concerned with the effects of climate change and are increasingly expressing the desire for climate-neutral alternatives for energy supply. Hydrogen is and I insist on the vital missing piece of the puzzle to help us to reach this deeper decarbonization and to reach it at a lower cost for the people. Few alternative technologies demonstrate such a breadth of technically viable decarbonization solutions as does green hydrogen. To reduce emissions from transport sectors such as maritime, rail, and trucking, to provide a route to seasonal energy storage, and to decarbonize the heating, as well for industrial as residential consumers. Prime Minister Narendra Modi has set the aim high to transform India into an energy independent nation by 2047, where green hydrogen will play an active role as an alternative to fuels such as from petrol and fossil-based products. Belgium, as Christian has already mentioned, it is the case for Brussels, but of course it's also the case for Belgium, with its limited offshore space, will need to import green hydrogen through strategic partnerships, but has a very rich hydrogen ecosystem with important players across the value chain. I believe that India's geographical advantage, combined with Belgium's technological advancement, offers our both countries an opportunity to work together while fulfilling our respective climate and clean energy goals. In addition to a favorable impact on the distribution of our respective energy mix, positive consequences are expected for the economy, such as jobs and, of course, reducing of our energy dependency. Both our countries have not only complementary strengths in the field of green hydrogen production, but we also, and that's very important, enjoy a long and a good relationship. Back in 1947, Belgium was one of the first countries to recognize the newly independent Republic of India. And this year, we celebrate not only the 75 years, of course, of India's independence, but also the 75 years of our diplomatic relationship. There is no better moment than now to celebrate our relationship and further explore together the real potential of what we can achieve together in the future. To fight against climate change and the development of new technologies to tackle this challenge are now part of our common agenda. We have already made some strides in this field. Last year, for example, the Indian Ministry of Renewable Energy and the Belgian authorities started to negotiate the extension of an existing MOU to foster concrete collaboration in the field of new and renewable energy. Green hydrogen is amongst the areas of cooperation high on the agenda, along, of course, with offshore wind energy and the next generation of batteries. In April, the Belgian company John Cockrell partnered with Greenco, a very well-known Indian company, to build a 2 gigawatt electrolyzer manufacturing plant to serve the local markets. In 2 weeks, I will participate together with our regional trade offices in RenewX, a trade show on renewable energy in Hyderabad. And in September of this year, a Belgian trade mission on clean energies and clean technologies organized by our regional trade agencies will come to India and will participate with a big stand in the Renewable Energy Expo India in New Delhi. And I would also suggest to already pencil down the date of this expo in your agenda, as it will give you the opportunity to interact in person. That's very important with Umicore and Solvay, but also, of course, with much more actors from the Belgian Renewable Energy Cluster. Finally, you are, of course, all invited to participate in the next Clean Tech Forum, which will take place in November 2022 in Brussels, and which will again offer you the opportunity to meet all the major actors in this field in one location. Ladies and gentlemen, to conclude, as you can see, the stage is set for the next step. And of course, now I look forward to hearing the views of Mr. Verma and the speakers of Umicore and Solvay on hydrogen's role in the energy system of tomorrow. I thank you for your attention.
Thank you so much, Mr. Pierre Emmanuel. Thank you so much for those words about the collaboration between India and Brussels and focused on hydrogen production. With that, I would like to invite Dr. Amit Verma, the Director of Energy, NITI Aayog, who gives a quick overview of the Government of India's hydrogen production roadmap and the National Hydrogen Energy Mission. So looking forward to hearing from you, Dr. Verma. Over to you.
Thank you so much, and a very good afternoon to Mr. Perry Animal Brusman, Consul General of the Kingdom of Belgium, Mr. Harshalingam, Ms. Monier, all the distinguished participants, the organizers of the workshop. Thank you so much for setting the context and elaborating the need for deep decarbonization and the potential areas of collaboration and working together between India and Belgium. So I'm delighted to be here and interacting with you, and I would be giving you the perspective of India's hydrogen program. I will start by saying that India is very well poised for becoming a global leader in green hydrogen production, as it not only has a ample RE potential, it has been a tremendous success in increasing its RE capacity, which currently stands at 111 gigawatt, including 55 gigawatt of solar. India also has one of the lowest levelized cost of energy for solar power. Along with this, India also has a necessary technical workforce, a large domestic market required to scale up the green hydrogen production and reduce the cost to make it globally competitive for exports. Currently, the green hydrogen cost is about $4 to $5 per kg, and it is targeted to bring it down to $1 per kg by 2030. I would assume that many of us are aware of the commitments made by our Honorable PM at various forums, including Paris and Glasgow, which has set the pace for decarbonization of our country. Even at the risk of repetition, I would specifically mention his declaration to launch National Hydrogen Mission in his speech on the eve of 75th Independence Day and the Panchamrit declarations at Glasgow. The Panchamrit declaration sets the goal to reach 500 gigawatt of non-fossil fuel energy capacity by 2030, 50% of energy requirement from renewable energy by 2030, reducing projected carbon emissions by 1 billion tons by 2030, reduce the carbon intensity of the economy by 45% by 2030, and the most important of all, becoming net zero by 2070. The current impetus which we might actually achieve net zero before that. Most of this won't be achieved if green hydrogen is kept out of the discussion. As Mr. Perry already pointed out, none of the technologies are as promising and has a wide gamut as green hydrogen. So therefore, green hydrogen is going to be an important energy carrier for India to realize its decarbonization vision. And India has already made known its ambition of being one of the global leaders in green hydrogen production and for being a global inspiration for clean energy transition. This will also have a cascading effect on the economy too, by creating green startups, green jobs for the green economy. From being an importer of about $160 billion of energy, India wants to position itself as an exporter of green energy. The declaration made by Honorable PM were followed by MNRE, the Ministry of New and Renewable Energy, by releasing the National Hydrogen Policy in Feb 22, which addresses many issues like granting open access for renewable energy, 30-day RE banking facility, making land available for green hydrogen projects in solar parks, allowing green hydrogen and ammonia in manufacturing zones and bunkers near ports for long shipping, and offsetting RPO obligations for RE used in green hydrogen applications. With the above context, it is amply clear that India has tremendous opportunities for using green hydrogen as a backbone for greener economy. The policy will be followed by a national hydrogen mission, whose draft is already being discussed with many stakeholders, and it should be out soon, which is going to make a roadmap for India on how it's going to move in green hydrogen. A well-rounded policy framework for green hydrogen will involve many aspects like demand creation, ensuring supply of created demand, providing impetus to research and management, setting regulations and standards, risk management, human resource development, and addressing international issues. So going into details of each one of them, the demand creation must initially focus on sectors which are already using grey hydrogen, like refining, fertilizers, and city gas supplies. Setting aggressive green hydrogen obligation targets within these industries, focusing on important checkpoints in the years of 2025, 2030, and 2035 will set the pace for other hard-to-abate sectors as well. The fertilizer and refining sectors have the capacity to meet about 50 to 70% of the hydrogen demand through the green hydrogen route in a decade. The harder sectors like steel, which needs to shift to DRI technology, the direct reduced iron technology, shipping, which needs to shift to ammonia-based engines, and land-based heavy transport, which needs to shift to heavy-duty fuel cells to make the use of green hydrogen widespread. All of these technological shifts will need a demonstration of technological feasibility through pilot projects and help shift from the current consumption of about 5 to 6 MMT of gray hydrogen to green. Current green hydrogen hubs can also be developed in areas where many industries are located, which can utilize green hydrogen. We have already seen the success of PLI scheme in solar manufacturing, and India is already targeting upward of 10 gigawatt of annual capacity in those schemes. Green hydrogen will similarly be benefited by PLI scheme, which will be focused on developing indigenous manufacturing capacities for electrolyzers, transport and storage infrastructure and fuel cells. And this is one of the very important areas of collaboration. While it is good to have technology agnostic policies, it is important to focus on the sunrise technologies as well. We all know that PEM and solid state electrolyzers are some areas which are very high in technological innovation and which needs to be worked together with. Alternate technologies like thermochemical and biochemical processes for developing green hydrogen should also be kept in perspective, because India is a biomass rich country and has a great potential of using those technologies for green hydrogen production. For all these technologies to develop, intensive collaboration and R&D with industry and institutes of eminence like IIT and ISC are being and will be supported by the government. For industry to invest in a country at ease, I would assume that they would need regulatory clarity and standards against which they will be held accountable. So that framework is also required. This includes framework for testing, storage, distribution, transport, and safety certification, which are globally accepted, because export is a very important key in this whole chain. In India, such standards will be defined by Bureau of Indian Standards and PISO, Petroleum and Explosive Safety Organization, which will conform to the global standards. Again, this is an area of international collaboration on how to come up with a green taxonomy and common standards so that the interoperability of the equipment and tankers and storage devices is easy. Risk for novel technologies include supply chain disruption risk. We've seen that during the COVID times, the technological risks, the resource crunch from land, water, and renewable energy, the safety risk, especially with the fuel like hydrogen, demand risk, and financial risk, which are all being addressed through approved policies, missions, and PLI schemes. Skilling for new technologies is also required, for which academia will need to update their curriculum. While this transition is happening, the focus on just transition for people employed in the sunset sectors has also to be kept in perspective by reskilling the workforce to join the new green economy. Even with all the demonstrated technology, I always believe the bottom line is always financial. The cost structure of green hydrogen is not conducive for large-scale adoption, and therefore various industries will need strategic interventions to compensate for cost difference and achieve required scale for making green hydrogen competitive. The 111 price point of $1 for 1 kg of hydrogen in a decade is well known, and many factors will contribute to make that happen. Looking into the future, there are two phases visible at this point of time. One, to prepare the indigenous manufacturing capacity for electrolyzers and other supply chain for green hydrogen, and which is likely to last for 3 to 4 years. The second phase, when the production of green hydrogen starts, reaching the market and the end users, both domestic and international users, start using green hydrogen. The estimated demand variance is very high. Many think tanks have come up with numbers, but it is expected internally that demand of green hydrogen may reach 10 MMT in the next decade, requiring RE and electrolyzer capacity of 50 gigawatt. So regulation of a sunrise sector like green hydrogen is always an intensive process, as course corrections may be required as the time progresses due to the lack of industry insight today. As various challenges, infrastructural, technological, financial come into play, right amount of nudging would be provided by the government for required course corrections. Therefore, regulation should be seen as an ongoing process here rather than as an one-off exercise. So in the end, I would like to emphasize that it is always challenging to anticipate and address all issues for an upcoming sector like hydrogen, which seems to have the brightest potential today as an energy carrier of the future to offset the carbon emissions And we must all work hard to ensure that it happens to save our planet from the vagaries of climate change and achieve the shared vision of its deep decarbonization. It must also be stated that India is determined to realize the vision of our Honorable PM of making India a global leader in clean energy transition, for which green hydrogen will play a very important role. Thank you.
Thank you, Dr. Varma, so much for your thoughts and insights into India's commitment to the production and export as well of green hydrogen, and looking at how again can collaborate with various stakeholders like industry, academia, as well as international interventions to address key issues like climate change that are becoming more and more evident daily, I would say. With that, I would like to invite Dr. Fabrice, the Director of Government Affairs, Electromobility Projects, and the Coordinator of Asian Affairs from Umicore. Dr. Fabrice, over to you.
Thank you so much. I hope you can see and hear me. Perfect. So let me first thank you for organizing such a timely event, I think, and also we are always impressed to see the ambitions of India in the field of hydrogen and the speed of change that we see. So it's a lot of opportunities for collaboration, and I hope I can give you in a 10 minutes or 15-minute slot a first feeling of what we do at Umicore in the field of the catalyst for the green hydrogen economy. So I always have to do a little bit of marketing, which is a short presentation of the group, but very short. We are a global materials technology and recycling group working on 3 big pillars. The first one is, I would say, emission control catalysts for the traditional cars that are still around, of course, for a couple of years to come. So it's also for light duty, but also for heavy duty vehicles. Second, we are a leading supplier in the field of the materials that you put either in rechargeable batteries or in fuel cells. So basically, when it comes to clean mobility, we can support both technology options. And last but not least, we are one of the world leading recycler of complex waste streams containing precious metals or strategic metals. Why do we say complex? Because if you look today at a car battery, or if you look today at a phone or a printed circuit board, it's very complex elements containing a lot of different metals, which need to be separated from the one from the other. So basically what you have also on the bottom of the slide is the breadth of Umicore metals portfolio that we're able to recover at our world-class facilities in Antwerp. Also, as a group, we are indeed Belgian by DNA, but like all Belgian companies, we very fast looked outside and expanded globally. I think this is part of the Belgian spirit. We are still European. If you look at the amount of people that are in the group, about 6,000 people are still located in Europe. But as you can see, Asia is, of course, a high growth market where we are investing, and both in terms of our research facilities, but also in terms of manufacturing facilities. In India, our presence is in the automotive catalyst sector, which is also using precious metals, by the way. And we are in Pune, and we have a very dynamic team at the Umicore Marketing Service in Mumbai that can support you with choosing our products and applying them to your technologies. So what do we do in the field of, I would say, fuel cells or electrolyzers? We are providing catalysts, so we are providing powders. It may not look as sexy as the final applications, but without these ingredients, your application does not work. It's a little bit like the silicon chip in a laptop. If you don't have the silicon chip, there's no laptop working. So this is what we do. So we are at the, I would say, upstream part of the value chain, the catalysts. And afterwards, our catalysts are sold to someone making an MEA, a membrane electrode assembly, which is later finding its way into the stack, and then later into the final application. So we are really at the start of the value chain. We enable it, and we enable it with various types of catalysts that you can see on the slides. Either catalysts that enable the fuel cells, so that's the conversion of the hydrogen and the oxygen into energy and water, or catalysts that enable the reverse mode, which is the production of the hydrogen that is so much needed for decarbonizing the industry systems all around the globe. In terms of metals that I use for these catalysts, they are based on platinum and they are based on iridium. Iridium, it's mostly for the anode part of the electrolyzer. We've been active in the hydrogen economy before it was called the hydrogen economy. It's about 30 years ago that we started looking at the catalysts that you can use for the fuel cells. So we have a long track record, I would say, over 30 years in the field. Of course, over the past couple of years, everything has accelerated, and we cannot say that hydrogen is a hype anymore. It's a reality, and it's happening right now. In terms of global presence, Asia is the center of the hydrogen world, as some would say. So you can see our presence in Korea, China, Japan, and India. And we also have, by DNA, a lot of R&D activity, of course, in Europe, because this is where it all started, where we have an activity in Hanoi in Germany, but we also have activity in Belgium and in Denmark. So looking at the different applications, they are not responding to the same business dynamics. Of course, what is, of course, today a near-term growth potential activity for the group is the mobility sector, where we are providing the catalysts that go into the fuel cells. And then at the other side of the slide on the right, you have the green hydrogen, which is a very vibrant but long-term growth potential opportunity. There's a lot happening, and there's still so much more that can happen. So this is where we look at it this way. And in the middle, you also have an important element, which is even less developed in terms of technology maturity, which is the technologies to transport the hydrogen as liquid organic hydrogen carrier. And what you can see on the bottom, and it should not be understated because it's very important, this is our possible services in the field of recycling, where we can recycle the fuel cells, we can also recycle the electrolyzers, and we can recover the metals. And in order to do that, we have a circular economy approach. Basically, I'm going to give you a few elements in order for you to wrap your head around how the market is developing. In terms of transportation and fuel cells, this is how we look at the market today. So, of course, there is a competition between fuel cells and batteries. Everybody knows about that. But if you look at transportation, there are also different mobility segments. If you are looking at light duty vehicles, which is the cars that we all have at home, it's just, of course, for us clear that batteries are going to be one of the dominating technology. But for those who would be looking for light duty passenger cars that can have a very large autonomy in terms of range of kilometers, there are not so many technologies that can comply, and there you can see fuel cell as the technology. But when it comes to high duty mobility, like the trucks, the vans, the lorries, the buses, there the role that fuel cell technology can play is clear to us, and there is a lot of advantages that can be leveraged. The technology that we invest in Umicore, it's proton exchange membrane, so PEM technology, and there we can see a huge market potential. Today, we estimate the market size at around 4 gigawatts if you convert it into energy equivalent. And we can see this expanding by close to 40 times within the next 10 years, even before the next 10 years, by 2030. So within the next decade, as Mr. Amit Verma was saying, there's a huge growth potential for the hydrogen economy all over the world. In terms of catalyst demand, you don't have 40 times more because, of course, as we grow the business, we also develop better products. And what we try to do is to have the same amount of performance with a diminishing amount of precious metals, because we have to be careful with this. This is a finite resource, it's critical raw material. And even though we are recycling, we still need to make the best we can in developing materials that are more performant, I would say. If some of you have ever driven a Hyundai Nexo, then it means that you've been driving with Umicore catalysts inside. But we are also, of course, developing our presence in other platforms at other OEMs in the world. We have running programs with different car making companies. But the one that is the most, I would say, visible, and the ones that we communicate about is our involvement since a long time with Hyundai Motor Company, and the fact that our catalysts are present in the cars. Something that you may not be too familiar about, so maybe it's interesting that I spent some time on it. This is the LOHC technology, and LOHC stands for Liquid Organic Hydrogen Carrier. What we are trying to do with this technology is to kind of solve the issues that we have with transporting compressed hydrogen all around the country or all around a region. We believe that there are ways maybe that can be made simpler, that would also require less investments in infrastructure, because you could use the liquid dispensing infrastructure that you have. So typically petrol stations, to make it simple. The technology is the following. The green hydrogen that is generated, we capture it into the form of a liquid organic molecule. This molecule is a liquid that you can dispense and move easily, very safe. It's not catching fire, for example, and you do not need to work in too complicated conditions in order to move it around. Afterwards, when you need to recover the hydrogen, you have a catalyst that is able to separate the molecule from the hydrogen, and the hydrogen is generated where and whenever you need it. And that's a very powerful technology. This technology is, of course, still being developed. And of course, we have a partnership for this technology with Anglo-American, which is a big producer of platinum group metals in South Africa, but also globally. And we believe that it's really worth it to look at what this technology can bring. We are not saying that this technology is going to solve all the problems and is going to be useful in all the segments, but it has such a high potential that we really want to make sure that we give the best in developing this technology. And of course, my overview of how we enable the hydrogen economy and the Indian hydrogen economy would not be complete without giving a strong point of attention to electrolysis, which is the star in all the countries today. As it will be well developed by my colleague from Solvay, there are various technologies when it comes to producing the hydrogen. You have alkaline technology, you have SOEC, you have PEM technology. At Umicore, the catalysts that we produce and that we commercialize for this electrolysis technology are PEM focused. But we are also considering other technologies in the screening that we do. But today it's mostly PEM. And there as well, we see a huge potential for development. I would say that if you compare to the fuel cell development, this is a couple times even more. As you can see on the slide, today, the production of green hydrogen by PEM, it's maybe 0.1, 0.2 gigawatt. There's a lot of course, capacity which is in the pipeline, but today it's below the gigawatt. And we estimate that within the 10 years, even less, we should go to 90 gigawatts. So the math is quite simple. It's huge in terms of growth potential. In terms of catalyst demand, this is less because it requires less catalysts, but still it is also a quite impressive multiplier from 0.3 tons to 6 to 7 tons of catalysts. So there, Umicore is, of course, investing the best we can. One point that I also want to stress here is that we may have been doing this for more than 30 years. We are, of course, not doing this alone and in-house everything. So we are dependent on a very vibrant ecosystem of technology partners all over the world. And we are always welcoming opportunities to collaborate wherever the technology is, be it in Europe, be it in India, be it in the States. We are always very much looking forward at doing open innovation with everyone. A couple of takeaways before I close, maybe the overview, and then I'm free for any questions you may have. We are very happy to see that there are strong government initiatives to promote the hydrogen-based economy. And we see that India is really taking a strong leadership role in the field, and we are very happy to see that, and we are very happy to be able to contribute. We see lots of opportunities in different elements of the hydrogen economy, be it in the mobility where we have been traditionally focused, but also in the production of the hydrogen, and to a medium long term, maybe the transport of the hydrogen with some technologies. At Umicore, we are very well positioned to play a role in that, and also to help any potential customers to choose the best products for the application and work with the best R&D team for the application. And with that, I would simply close it. I'm very happy to answer any questions you may have later this morning. And thank you so much for inviting me.
Yeah, thank you, Dr. Fabrice, for your insights, and it's great to hear about your 30-year-old long history with hydrogen and your commitment to Asia and India as well. And also very interesting to learn about the liquid hydrogen, organic hydrogen carrier solution that you're developing. We will come back to the Q&A session. I think we do have a question for you. But before that, I would like to invite Mr. Vincent, who's the head of the Worldwide Sales and Development Director for Green Hydrogen at Solvay. Mr. Vincent, I think once you're done, we'll get into the Q&A session as well. Thank you.
Absolutely. Well, thank you so much for the invitation. Thank you so much also for the introduction made by Mr. Brusselsmans and Dr. Verma. And also, after hearing what Fabrice Tassin has indicated from Umicore, we really confirm all those elements. It's critical to act now for decarbonization. It's critical to do it in a structured way, and it's critical to understand that the materials will play the key role to enable this transition to the green, let's say, economy. I have a bunch of slides that I will be presenting. You will see that they cover a lot, and it's the result of what Solvay has, let's say, started to capture some years ago and has crystallized into the form of a green hydrogen platform. So let me share the screen here, and let me see if you see it. Just a second. Hop. Let me just go directly.
We can see your screen now. Yeah.
You can see the screen. Okay, let me go into presentation mode. Okay, there we go. Yeah. So well, again, thank you for the invitation. I really look forward to this exchange together. And here, let's really work at a high level and then go down step by step to the material part. Who is Solvay? Well, Solvay, as indicated in the introduction, is one of the oldest chemical company, international company. We have reinvented ourselves for 150 some years, and today we are representing about 10 billion in sales, with about 21,000 people, active in 63 countries, with a lot of industrial sites. And what is really, I think, a major change that we have observed in the chemical world is that we need to work on sustainable solutions. This is really, today we've reached 53% of our sales related to sustainable solutions, and it's the result of a special, let's say, program related to the selection of research and developments that led to this level. And to be even more sustainable, we have created the Solvay One Planet, which is really a way to organize ourselves to protect the climate, to limit the climate changes, to preserve the resources, and to foster a better life. Those are really the value of Ernest Solvay, the founder, and it's being, let's say, embraced today by our CEO. What do we do in India? Well, like you see here on the slide, India has been a place where we've been active for many, many, many years, and we have different sites, different productions. You see on the left-hand side that we produce some guar material, but we produce also extremely high-end materials like PEEK and polysulfones. We have the Research and Innovation Center as well. We produce some catalysts as well, and we have some corporate application labs that we can tap into to develop with you locally the solutions for the future. We are also active with specialty polymers, in terms of distribution of those products and commercialization of what we do there, and also produce some surfactant and alkoxylate. What does it mean today in terms of employee? And I was looking at the Umicore number. It's about the same number. So 600 people there, and with a significant level of sales already there. So we are present. We are part of the network and the industrial network there, and we look forward to, being closer to all of you. Recently, so early last year, the executive committee has decided to create what we call the platforms. The initial platform was created to cover the battery materials. Another one was then created to cover the thermoplastic composite materials. And last year in February, we officialized the green hydrogen platform. And what's the goal of a platform? Well, we are an extremely diversified company with a lot of products. And we realize that it's difficult for our customers and prospects to see and find, what they want in the myriad of solutions that we offer. And so the platform is really a pretty small, agile team that is focusing on addressing those questions you would have and finding the solution within the group. And you will see later on a lot of the solutions that we can offer. So the platform for us is created, provided it will have a substantial future that will drive the growth of the company. Just to give a number, for us, the green hydrogen platform has a sales objective that is substantially higher than 1 billion euro. It's not negligible at all, but we believe that all the elements are there. We structure ourselves with, a head of technology, a head of marketing, a head of industrial, myself for the commercial and business development. And you see here the head of industrial function. Why is it so? It's because what we have today is substantially insufficient to meet the market needs. We've heard it in the introduction, we've heard it with the Umicore presentation. We need to get from you a vision of what the needs will be so that we can also integrate that in the industrialization of our products. But what is really the scope market-wise? And this is what we have here. This is a pretty interesting scope because, we want to be the solution provider through material supply to reach, of course, the green H2 long term. And we have to be active at a lot of different levels, and we know we can do it. And you will see later on which products. We want to be, and we are active at the energy storage level, at the electrolysis level. In the infrastructure, you will see something I think will be, a pretty interesting surprise. And then, of course, at the end users. And what used to be a driver for our developments, which is the fuel cell, is now becoming, of course, a really important application for our products. But to feed the end users with H2, you need first to make the green H2. And this is where we will play a substantial role. So what do we want to do? Where do we want to play? The platform scope starts at the energy storage, which is the electrical energy storage, to be precise. We've realized that the intermittent supply of renewable electricity has to be addressed because the electrolyzers cannot, as of today with the current technology, absorb huge variations of electricity and energy. And so the energy storage in the form of what we call the redox flow batteries that will complement the lithium-ion, technology that we see today. The redox flow battery will be able to store energy between 4 and 12 hours based on the size of the electrolytes that we will flow around the membranes. And there are different technologies there. You will have vanadium, you will have iron, you will have zinc-based or organic-based redox flow battery. All of them will need an ionomeric membrane that will move the ion from one side to the other side, to the one electrode to the other electrode, but with substantial, mechanical performances and diffusion performances. And there you have the ionomers. They could be of different types. Fluorinated, we make those. Aromatic, we make those as well. But this is usually the forgotten, let's say, part of the equation, the redox flow battery. So keep an eye on it, because for PV, you might have a lot of irradiation during the day, but then what do you do during those, let's say, 6 or 8 hours of, let's say, night? This is where the redox could do, let's say, great. By the time we've provided, let's say, that constant supply of electricity to the electrolyzers, we enter into the field of electrolyzers. And there, what you see as products, which are listed on the bottom of this slide, is that the electrolyzers, we for sure focus on the membranes, and you will see later on some components. But the electrolyzers today, the way we look at them, they are like a big piece of, let's say, equipment full of steel and metal. And we believe there's a substantial role that can be played there to reduce the quantity of metal by using plastics, polymers, engineering, and specialty polymers, so that you can make the electrolyzer faster, reduce the weight by maybe 60%, and move those electrolyzers from a site of production to a point of use with a normal mean of transportation, even for a 5 megawatt alkaline technology. So the polymers are important for what we call the balance of stack, but also the balance of plant. But we also have then to look at which polymers we will use in the membrane. And it's a function of what technologies will be used. Mr. Stassin indicated the PEM as a really important one. And it was also our view some years ago. But over the last 2 or 3 years, we've realized that there's a huge amount of work that should be injected into the development of the alkaline diaphragms, and in the future, in the alkaline anionic exchange membranes development. And we are active there. We are also active on the solid oxide technology, which was initially fuel cell, but more and more we see the electrolyzer technology based on solid oxide. And there we supply as well some key products. We'll see later on which one. Infrastructure, two things that are key here. We believe that for the storage, we have to consider 2 elements. The first one is large storage, you will see, and then smaller storage. Smaller storage was that, what does it mean? It means the H2 vessels in a car, for instance. A 6 kilo quantity of hydrogen will require an H2 vessels that will be about 70, 80 kilos. Most of it would be carbon fiber. Guess what? We make carbon fibers. We make the composite materials that could be either thermoset or thermoplastic. And so we believe that by injecting our knowledge there, we can develop the right materials for the H2 vessels, composite ones, to also meet the recyclability targets. And then for the end use, you have all the different things that we have heard before. And I think that what has been mentioned is extremely, let's say, the same for us. Our materials are, again, for the balance of stack, the balance of plant, and for the membranes. What is interesting here to see is that the membranes for the fuel cells, the ionomers, today, those products are available, with limited quantities. Large volumes will not come out of the blue. We have to build the installations, the sites to manufacture those materials, because they are not yet used, at scale in other fields that we can take from. So we have to create everything, from, the base we have today. And this is where we need to understand which ambitions, are there, and what commitments can be taken by the actors, so that we together can de-risk, our investments, and we can meet the needs of specific materials. More precisely, let's look at the different technologies that I've already discussed. The alkaline technology, we believe that by 2030, there will be about 45% of market share for this. It will require a specific diaphragm. Today, we are already active there. with a polysulfone material. And if you remember what the first few slides said, we produce polysulfones as well in India. So India could play a role as a producer of those key components for the alkaline electrolysis. And we also see that since the polysulfone is used as a diaphragm, usually on a supported net of PPS, which is the Riton polyphenol sulfide, well, we believe that those PSU or PPS materials are, well, in fact, they've been demonstrated as suitable material for the construction of the stack. So imagine a 70-ton, stack for 5 megawatt electrolyzer could be reduced to about 20 tons by the use of plastic. The parts could be big. They could be injected about 2 meters in diameter. It would be about 35 kilos per part. But this is something we can do. So you can already limit the shavings, the machining. You have a part that is ready to use in your system. So this is really interesting. And also on top of it, your ramp of temperature increase for the stack will be substantially faster. So you will have a more reactive alkaline electrolyzer. So this is what we can bring. And we can do the simulations for the materials to optimize the part, the way we inject it, the way we make them, the material selections, as well as the leachables that could eventually contaminate some of the byproducts or the products of the electrolyzer. For the PEM, we make the fluoroionomers, and they are used as the membrane, the key material of the membrane, which is the proton exchange membrane. In that case, is made out of a special product, a fluoroionomer called perfluorinated sulfonyl acid, the PFSA. We've been making those products for 25 years plus. So we know what we need. We also understand the permeation issues with H2. And we also realize that the temperature will go higher, the pressure will go higher. We even heard, that through that, the current densities could increase dramatically. So increasing the efficiency of use of the materials. And there again, for the balance of stack and the balance of plant, we can increase the lifetime of the units by having the right materials. Today, and for electrolyzers, we'll be targeting, 80,000, 100,000 hours, so 8 to 10 years of operation. What could be the weak spots are some materials that are not fluorinated, for instance. And there we have some solutions because we have, for instance, for the PPSU, which is the gasket material, we have been using those materials in water transportation for 25 years plus with hot and cold cycle and so on. So we know we have good solutions there. And the last technology, solid oxide, this is where we have all the cerium-based materials. Usually it's called a cerium gadolinium oxide. And we can then, through those compounds that we make, reduce the operating temperature for about 700 degrees C to 600 degrees C. And so it increases also the dynamic of the system. And this is a pretty substantial, let's say, development. And we believe 10% of the market share by 2030 for this specific application. This is just a recap of what I indicated, but for sake of time, I'd like to just jump to this one, which is the salt mines. Solvay, in fact, has been making soda ash since the beginning of the company. And to make the soda ash, at some time you have to extract the brine from where the salt mines are. And this leaves a cavity. And that cavity today is used for the storage of natural gas. And those are huge cavities. You can put the Eiffel Tower in one of them, for instance. And what we've looked at is that the need for H2 storage by 2030 in Europe will reach about 72 terawatt hours. Knowing what the volume of a cavity is, it would represent 600 salt caverns. And it would be more than 1.3 million tons of H2. I've heard that India wants to export, and this would be a place where you could store the H2. And why would that be of interest? It's because when you look at the cost of the storage of hydrogen into salt caverns, this is the cheapest option you can think of. This would help, to to address fluctuations of supply, fluctuation of demand, and for a time period that would be maybe at the 6 months level, but it's not something that you would consider, let's say, for really extremely high dynamic situations. But it's more, you know, a reserve, a strategic reserve that could be used with some, of course, dynamic. We are making those caverns as we speak because we need the salt. And the sooner we know we have to reserve caverns for H2 to avoid cross-contamination with potentially, let's say, natural gas, the sooner we'll be able to activate those caverns to secure the H2 storage. The key learnings, I would say, related to our 25-year plus in the fuel cell and H2 business is that the materials, like Umicore has indicated, will make the difference. They will make it happen. But today, the quantity of materials that are required is substantially, you know, higher than what the market can supply, what the industry has been, let's say, invested in terms of capacity. So that's really important to know. There will not be enough material if we don't anticipate the needs with investments. The current materials are, let's say, a good base, but we want more R&D, we want more partnership, and we want also to close the loop. We want to recycle that product, that ionomer, that bipolar plate or whatever. It has to be part of our designs as we work together. So I underline the fact that we need anticipation of the needs. We need to know what you will need. We need to know how we will get there together so that we de-risk the investments. And you have a full commitment from the company to work on the development, the improvement, and to meet the volume needs to reach decarbonization. We have no choice but to do that together. Thank you for your time. Any questions, feel free to answer.
Thank you, Fabrice and Vincent, you know, again, you know, for both your comments, and, you know, great to see that, you know, there's a lot of history in terms of what you've already been doing, as both your organizations have been in the industry for 25, 30 years, and it'd be great to, you know, bring in those learnings, you know, and not reinvent the wheel, and, you know, start, you know, collaborating with India, looking at our future as well. Yeah, so it would be great if anybody has any questions. I think we have one question already for Fabrice from Mr. Sanjay Kumar from IIT Indore. He just wanted to know what kind of LOHC are you exploring, and are you working with any Indian institutes already?
Hello. Yeah, the LOHC technology that we are looking at, it's a technology that is developed in partnership with Anglo-American. And in terms of collaboration opportunities, we are looking at all the open innovation options that we have. I cannot comment on which institute is collaborating with us, but if you would like to know more, I'm happy, of course, to put you in contact with the LOHC team within Umicore and facilitate a contact.
Great. So also just want to open the floor to Dr. Verma, if you have any questions, or even if you or Fabrice or Vincent, you have any questions for Dr. Verma also, please feel free.
Maybe I just had a comment on electrolysis technology. As Vincent said, there is a full portfolio of different technologies which all have the pros and the cons. And at Umicore, we believe that every technology should be developed because different test cases mandate different technologies. So I'm very happy to see that there's a strong Belgian player looking at all these technologies. That's really good for us as a Belgian company. And then on the storage, personally, I was not aware of the big needs that Vincent has put on the slides, but it's true that there are different also here test cases depending on for how long you need to store and how dynamic the storage has to be. But salt caverns, they really have a strong role to play. This is also what Umicore believes, even if we are not active in this field, of course.
Thank you. As a matter of fact, this is something that is not well known. Mm-hmm. But when we look at the, again, the intermittent supply of H2, maybe a vessel will come, maybe they will be stuck and so on. Those caverns, provided they are understood as a medium of storage, I think they will play a substantial role as, let's say, could be an active buffer, to also maintain the pressure and so on the network, because keep in mind that those caverns will operate most likely at about 200 bars of pressure. So this is a substantial buffer. It's like something that we need to show to the industry. We're working with some operators of the network so that they can start reflecting on how to integrate that in the management of the needs for H2.
Thanks. We have a couple of questions. Sorry, Dr. Verma, please go ahead.
So yeah, if I may, so both the presentations are wonderful and gave a very good insight about the latest technological developments. My question was about the LOHC, whether the energy density decreases when you use that. The hydrogen itself has a very low energy density, and how is that extra weight of the organic fuel affecting the cost of transportation? I mean, if you have done studies on that.
I would be very happy to provide you with more information, but in general, it's true that as soon as you hydrogenize a big organic molecule in terms of energy density, there is a penalty, which actually restricts the LOHC technology to some very specific use cases. The storage of hydrogen using LOHC over a long period of time, as Vincent has shown on the graph, you cannot compete with the salt caverns and other technologies. But if you want to store limited amount in a very dynamic case over small distances, for example, then I'm putting all the best conditions together. Then of course, LOHC is one of the technologies. So this is always the issue that we have with the hydrogen economy, is that a lot of different technologies will be needed, which does not make it easy to understand the field. But for electrolysis, very different technologies will be needed. For storage and transport, very different technologies will be needed. There's a lot being done for the moment at the Hydrogen Council, of which Solvay and Umicore are also members, looking at all these technologies, because there's a need to also better define which technologies merits which other technologies. So there, I would say on storage, this is maybe on storage and distribution, this is maybe one field of the hydrogen economy which is going to get a lot more explanation in the near future, because this is the least advanced in terms of technology clarity. But as soon as more is published, I would also be happy to bring it back to you.
I'd like to really reinforce this comment. Material-wise, the H2 storage will require huge quantities of carbon fiber, for instance. How you transfer the load, associated to the 700 bar, let's say, pressure that you have, and how do you transfer that to the carbon fiber? How do you optimize the carbon fiber to use less? How do you take the aerodynamic expertise that we have and bring it, to the automotive industry with a factor of cost that is totally different? If we consider the H2 tank vessel's potential and compare that to the available capacity of carbon fiber, there's basically no carbon fiber available today that can do that. We need to invest a huge amount of quantity of carbon fiber. And this is for pressurized vessels. And then you have the cryo-compressed vessels, and then you have the liquid hydrogen. And the liquid hydrogen is what we are working on as well. Keep in mind, it's 20 Kelvin. So minus 253 C, and there you need to understand the material performances at that, let's say, extremely low temperature, and this is complex. But in Belgium, we have some good competencies as well for the studies at those low temperatures, and we are studying if liquid hydrogen, can be transported with the right, let's say, plastics and polymers. We are working on that as well. So this is just to give you the ultimate goal. This is to decarbonize aviation.
Thank you.
Thank you. I think we have a couple of questions from Mr. Pradeep NG. Mr. Pradeep, would you like to maybe unmute yourself and ask the questions, or would you like me to direct the questions for you? I think Mr. Pradeep's question, one was to Mr. Fabrice. Where do you source the raw catalyst PGMs from? And do you have any agreements with Anglo Amplat? I think that was one of his questions.
Yeah, there are not so many companies and so many countries which are providers of these metals, so it's easy to make the math. But what is also important to recognize is that at Umicore we have a strong history in the field of automotive catalysts, which are also using the same materials, the same elements, that is based on the platinum. That means that since we also have a recycling activity, there's a part of the metals that we use that are actually not primary anymore. They are secondary in the sense that they are coming from a recycling feed. And there it's very important to insist on the fact that each time you produce a metal by recycling, it's better than producing it by primary, because it means that the CO2 footprint is also much lower, because you are extracting a metal from a very concentrated source, and you're also not transporting the metal over long distances. So this is a little bit the supply strategy of Umicore. We cannot get all the metal from recycling, but actually in the field of automotive catalyst, you have already a lot of recycling, by the way. And when it's not possible to get it by recycling, then you have to tap into the typical providers. The name Anglo-American has been mentioned. I also wanted to stress that this LOHC technology development that we do, this is a development that we do with Anglo-American. And I had forgotten to mention that this is also something that is being done with Hydrogenius, which is always difficult to pronounce for me, but that's a technology which is at the forefront of the LOHC technology.
Another question from Mr. Pradeep to Vincent as well. How is your fluoropolymer membrane different from Nafion, NEF-I1 Nafion?
Absolutely. Well, thank you for the question. Both of them are perfluorinated molecules. So it's like a piece of TFE, if you wish, PTFE, but you have some special chemistries. The Nafion are usually called long side chain. So you have a pretty long pendant group with the sulfonyl group. This is long side chain. For Solvay, the Aquivion, which is the brand name, is a short side chain. So it's a smaller, let's say, pendant group. And this change of chemistry related to the way we manufacture the components of the polymer, they are called the monomers. If you have a short side chain, you imagine you can put more of those functionalities in a given length or a given volume. So we are, by definition, providing a higher conductivity material. And we can also improve the operating temperature by 40 degrees C. So respect to, let's say, the non-short side chain products that would have a limitation at around 90, 100 C, we can really go for 110, 120 C, because we have what we call a short side chain technology. And this is really substantial in terms of improvement of performances of the electrolyzers, but also for the cars. A fuel cell car that can operate at 110, 120, you can circulate the coolant at higher temperature, and then the radiator can be smaller. So a truck that will be a 200 or 400 kilowatt, let's say, system could have a reasonable, let's say, size for the radiator, which is usually the limiting factor today, because the radiator is the only place where the heat can go away from the system. There's no more the tailpipe emission. And so having the ability to work at higher temperature, because of the chemistry, because of the monomer, because of our expertise, well, I think this is where you see a benefit.
Thank you.
I would be more than happy to enter into those details with whomever wants to
Sure.
approach.
We'll facilitate that connection post session if required. I think we have time for a couple more questions. Mr. Sanjay Kumar, maybe you have a couple of questions. You want to unmute yourself?
Thank you, Asa. Good to see it's a good involvement from the government, from the Consulate General from Belgium is there, and Dr. Verma from Niti Aayog is also there, and industry people, and I hope like many academicians are also here. I'm Professor Sanjay. I'm working in the area of catalysis and hydrogen production at IIT Indore. So I'm very happy to see like most of the presentation, mostly the electrolysis part of hydrogen production is mostly emphasized, but this time Fabrice has mentioned about the LOSCs. So I have asked, in fact, this question, like what kind of specific LOSCs are they are exploring, because there are so many of such systems are there, like the carbon-based methanol or ethanol or ethylene glycol or glycerol. And in fact, ammonia has also been explored, and is being also explored. And related to this question, like I think you mentioned about the different type of precious metals using as catalyst. So exploring some low-cost catalyst in this area.
Maybe I can comment on the precious metals.
Yeah.
So at Umicore, we have, of course, a very ambitious development program of the catalysts, where what we try to do is to reduce as much as possible the amount of precious metals that we use, because they are expensive and because they are precious. But this is, of course, requiring a lot of advanced material science, and you cannot expect disruptive developments in the field. It's more evolutionary than revolutionary. So we try within the next decade to diminish the amount of precious metals. If you look at international roadmaps, they are typically trying to reduce by 20 to 30% within the next decade. Of course, different companies may be either less ambitious or more ambitious. I cannot really comment too much on that. But this is mostly evolutionary research. Now, when it comes to jumping to not using at all the platinum catalyst, for example, or the iridium when it comes to PEM, it seems to be extremely difficult to do that substitution step. Then it would be easier actually to consider other electrolysis technologies. That's why I was happy that Vincent gave the full overview of all the electrolysis technologies, because we don't believe that PEM is the solution to everything anyway. But in terms of substitution, really jumping from containing precious metals to no precious metals within the PEM family, we do not see this happening.
If I may add, let's say a PEM can work at 2 amps a square centimeter, current density like that. We together, as the ionomer producer and the catalyst producer, we need to see how we can go to 4, 5, 6, because it's not only the catalyst itself, it's how it is, let's say, how does it behave in its context? How is it, let's say, how are the protons conducted to the surface and things like that? So it's really a puzzle that has a lot of dimensions. And should we be able to increase the current density by a factor of 3 or 4 indirectly per watt or kilowatt or gigawatt of installed PEM, you will reduce the catalyst load, but increase really the performances and the dynamic of the system. It's a combined effort. And I was explaining the short side chain, the long side chain. It's all about those things as well, with the interaction together with the catalyst. It's a complex balance we have to strike together.
It's a system. Huh? It's a system, yeah.
And it includes the recycling as well, huh? Because the ionomer is a scarce resource too. How do we recycle that? We don't have all the options. Should we have the option? Yes. How? We work together. Really, we are the early phase of that, but we've recognized that the ionomer, there won't be enough. So we have to work on recycling as well.
Okay. One short question related to this, like it is to Fabrice. Like you mentioned about LOSC. So are you also proposing it for onboard hydrogen production?
I'm sorry, I missed you for 2 seconds. Can you repeat to me?
So for LOSCs, you have shown one cycle, which is, so are you also proposing it for onboard hydrogen production?
I cannot really comment on that because this is still a very low maturity, and we are looking at all the options. So it's not that we are not looking at things and looking at others, but there are some confidentiality that I cannot really disclose for the moment. But LOHC is still, as I said, very low maturity in terms of technology. So you can understand that then we look at many different options because it's low maturity. But in terms of the chemistry use and the test cases and the use cases, for the moment, I can't really disclose too much.
Yeah, because at the
Mr. Sanjay, sorry, I think we're running out.
Yeah, sir. Yeah.
I'll definitely connect you to Mr. Fabrice and Vincent for further questions.
But please, yeah, reach out to me, and then I can put you in contact with the LOHC team, and they better know because it's developing so fast that sometimes I may be lacking the latest information. But we're happy to connect you.
Yeah, thank you, Fabrice and Vincent. With that, I would like to kind of invite Ms. Patricia Motte, the Trade and Investment Commissioner for India at Hub Brussels. Yeah, Patricia, over to you, and then we can wrap up.
Thank you, Harsha. Well, I will wrap up very quickly this very interesting day and presentation. First of all, I would like to extend my very warm thanks in the name of Hub Brussels to the honorable speakers for their keynote addresses. So Mr. Verma, Director of Energy at NITI Aayog, and our Consul General in Mumbai, Mr. Brusselmans. We were also very proud to have the chance to have two flagship companies from the Brussels region share their expertise and solutions. So Mr. Vincent Meunier from Solvay and Fabrice Tassin from Umicore. We would like to thank our industry partner, GBI, who co-organize everything today with us. And of course, each and every one of the high-profile delegates who are attending this session. Just a quick note to re-clarify what Hub Brussels is. We are the Brussels arm of the Belgian Trade Office. Belgian Trade Office is composed of Brussels, Wallonia, and Flanders. And we are the Brussels Agency for Business Support. Our mission is to foster business and collaboration between India and Brussels, the capital region of Belgium. I will pass on context of our teams because we basically want to continue this conversation with you. We are available in India and in Belgium to help keep connect the dots between India and Brussels. Thank you.
Thank you, Patricia. And I would like to again also thank Dr. Verma and Ms. Pierre as well for joining us today. I've also dropped my email contacts for anybody who wants to reach out to Vincent or Fabrice as well. Please feel free to reach out to us at Global Business Inroads, and we will be happy to facilitate any further discussions between the two companies and yourselves. Again, thank you, everybody, and looking forward to taking forward this green hydrogen agenda forward. Thank you, Dr. Verma, as well again.
Thank you.
Thank you for the initiative. Really nice. Thank you.
Thank you. Bye-bye.
Thank you.
Bye-bye.